First of all, on this slide, we'll cover a few of the established and well-known fabric topologies. However, it is worth noting that each of these topologies is somewhat loose, meaning that you can mix and match and play around with them, and there are no strict rules saying thou shalt do this or thou shalt not do that. And of course, some are more common and more popular than others. Anyway, let's get on with it. First up, the mesh or full mesh topology. As we can see with mesh topologies, every switch in the fabric is connected to every other switch. This means that each switch is only one hop away from every other switch in the fabric, giving high performance and high resiliency. These days though, it's not that common to see full mesh topologies, especially in fabrics with a lot of switches. A major reason for this is that full mesh topologies quickly eat their way through switch ports for ISL connections, especially as the number of switches in the fabric scales. In our 6-switch fabric on the slide, each switch uses a minimum of 5 ports as ISL ports, 1 port or 1 ISL to each of the other 5 switches in the fabric. Imagine if we had 12 switches in the mesh, that would be 11 ports per switch consumed for ISLs, and that's assuming we're not trunking ports between switches. Clearly this can easily get out of hand, but if you want the lowest latency and highest resiliency and you don't care about losing ports for ISL connections, then mesh topology might be the one for you. Next up, cascade. Now before we go any further with cascade topology is an abomination and it should be banned. As we can see in our diagram, cascade design connects switches in a simple row, and it's neither scalable nor performant nor reliable. As a quick example of the lack of resiliency inherent in the cascade topology, if switch 2 in our diagram fails, it effectively isolates switch 3 from the rest of the fabric. Pretty rubbish, and it should be avoided at all costs. Nobody deploys cascade. Now let's talk about ring topologies. Now then, I've drawn our ring topology in the diagram this way on purpose. I know it doesn't look too much like a ring, but I've done it to show that it's almost exactly the same as the abomination of a topology that is cascade. But ring topology has one major difference. The switches at either end of the row in the cascade design are now connected to each other, forming a ring. And this seemingly insignificant additional connection makes a whole world of difference on the resiliency front. Now, if the same switch 2 fails on us, switch 3 is no longer isolated from switch 0 and switch 1. So ring topology is way more resilient than cascade. Sadly though, on the performance and scalability front, ring designs are still pretty poor, and anytime you want to add more switches to a ring topology, you've got to break the ring. Kind of like cascade design, ring is extremely rare in the real world. Now for the daddy, core edge. Core edge is easily the most popular fabric design in the real world. If you know anything about Ethernet networking, you might well be thinking this looks a whole lot like star or hub spoke design, and you'd be right. The essence of fiber channel core edge design is a switch at the core or the center of the network, with all other switches connecting to the core via ISLs. Now remember back to when we said that each of these topologies was only a loose topology? This is particularly the case with core edge design. For example, the way that fiber channel protocol works, it's perfectly acceptable to have more than one switch at the core and both switches fully active. Also, there's nothing special about the core switch. Sure, people tend to place director class switches at the core and have edge switches as the smaller workgroup type switches, but this doesn't have to be the case. The switch or the switches at the core don't need to have any special roles within the fabric either. However, a common approach to the core edge design is to have target ports like storage array ports and tape drive ports connected into the core, with initiator ports such as hosts connected to the edge switches. And this approach happens almost by default if you're deploying blade servers with embedded fiber channel switches within the blade chassis. These embedded switches become the natural edge of the core edge design and lend themselves nicely to being connected to a core switch with storage and tape devices connected at the core. Anyway, enough about topologies, let's mention fabrics and fabric services. Multiple switches connected together via E-ports form a single common fibre channel fabric, and we show this in our updated diagram. All 7 switches in our diagram form a single fabric. Every switch in a fibre channel fabric also participates in providing a common set of fabric services, and there's a whole bunch of fibre channel fabric services defined in the standards, but only a few of them that you really need to know about. First up is probably the name service, sometimes called the Simple Name Server, or SNS for short. The name server maintains a dynamically updated list of all devices registered and logged into the fabric, making the name server the go-to guy for all information about devices on the fabric. Every device that connects to and logs into the fabric is required by the standards to register with the name service, and every switch in the fabric holds its own local copy of the name server database. And it's this name service that is fundamental to implementing zoning, which we'll cover in the next slide. Other services include the Fabric Logon service, the Fabric Controller service, the Time server, and more. But you really have little to do with them and don't need to know them for your CompTIA Storage Plus exam. So with that, let's move on to zoning.